Hi, good afternoon. By now, we have gone ahead and covered the following in linear algebra. What are vectors? What is a linear combination of vector? What is linear independence of vector? We went ahead and from linear independence of vector, we talked about spanning the entire vector space. We also went ahead and we talked about how can we use to show whether vectors span the entire vector space, whether some vector belongs to the span of the vector or not. And then we talked about basis and dimension of vector. Further, we also went ahead and we talked about rank using linear algebra. And we said that we can also go ahead and define rank using matrices and determinants. So we gave various definitions to go ahead and define rank in vectors. Now, all of this is very important from the perspective of an IIT JAM paper, because we have, as we saw, got a lot of questions related to vectors in the paper 2021 from this topic. Today, I'm going to continue with it and I'm going to talk about linear mapping. This is the last topic from linear algebra that holds a lot of importance. So the question that then arises is, what is linear mapping? Now, assume that there are two vector spaces. Let X and Y be any two vector space. Now, when I'm saying that X and Y are vector spaces, they satisfy my closure properties. Okay. Now, given that X and Y are my vector spaces, we define a mapping. So please write down. A mapping is a function that goes from X to Y. So it is called linear mapping or linear transformation if it satisfies two conditions. The first condition that it should satisfy is that for any two vectors, u and v, that belong to your vector space X, when I go ahead and I find u plus v, I will show you, don't worry, but we should first understand the definition. When I have f of u plus v, it should be equal to f of u plus f of v. This is the first condition. The second condition for it to be called as a linear transformation or a linear mapping is that for any scalar k and vector u belonging to X, f of ku should be equal to k f of u. Now, please notice here, if I have this condition and I have this condition, can I go ahead and combine these two conditions and say that any linear mapping should satisfy this condition? f of k1 into u plus k2 into v is equal to, because to satisfy the first one, what do I want? That you should be able to add them individually. First one plus the second one. So I should be able to add them individually. Let's add them individually. What do I get? F of k1u plus f of k2v. And now I should be able to bring this scalar out from the second condition. So this should be k1 f of u plus k2 f of v. So for linear transformation or linear mapping, any two vectors u and v that belong to my vector space, I must have this condition being satisfied. This is one condition. It's written as one for these two conditions together, this and this. If this condition is satisfied, then automatically it is a linear transformation. Now, please understand. Suppose I tell you that, my vector in itself is a vector of zeros. And, whenever you put 0, you also get 0. So because this is the condition that you are just considering a vector of zeros, so f of v will also be 0. So f of u plus v can be f of 0 plus 0, can be f of 0, which is 0, and f of u plus f of v can be 0 plus 0, which is 0. So, even if I multiply with k, I will get k into u, 0, which is 0. So basically, any vector which is a 0 vector will automatically be a linear transformation. So this is a very important but a trivial result. Please write down that every linear mapping takes 0 vector into 0 vector, and 0 vector is a part of every linear mapping. Now let's take some example and see if they are part of the linear mapping or not. So take this example. Suppose I have a function that goes from R3 to R3. So supposedly what this function does is the following. Whenever you put vector x, y, and z into the function, the output that you get is x as is, y as is, but for z you get 0. Whatever z you put, whatever z, you will get 0. My question to you is this linear transformation? Is this a linear transformation? That is what my question is. So what I will do is, to answer this question, let me go ahead and consider two vectors. So I consider a vector u. This vector u has 3 elements, a, b, c. I consider a vector v, and this vector also has 3 elements, a dash, b dash, and c dash. Now what is the first thing that I have to do? I have to find f of u plus v. So this will be f of u. U is a, b, c, plus v. V is a dash, b dash, c dash. And then I have to apply the function on top of it after adding. So, we know that in vector we do component by component addition. So a gets added to a dash, b gets added to b dash, and C gets added to C dash. We know this, right? So I can do this. So simple, this will be A plus A dash, comma, B plus B dash, comma, C plus C dash, and I am applying a function on top of it. And what is the role of the function? What is the function really doing? That whenever anything goes inside the function, the output of the function is X as it is, Y as it is, and 0. So when this goes inside the function, the output of the function will be A as it is, in the first element as it is, the second element as it is, and the third element becomes 0. This is what the function is doing. We see here. What is the role of this function? The role of this function is it takes this, whatever vector you put inside the function, and after taking that vector, it gives you the output as X, Y, and 0. So this is what I am doing. This is the vector it took. And then when I applied function on top of it, it gave me the first part as is, second as is, and then 0. So if I go ahead and I take this, can I go ahead and can I split this? Can I say that this is A, B, 0 plus A dash, B dash, 0? Because, you know, this is just component by, if you add this component to this component, you will get this. If you add this component to this component, you will get this. And if you add this to this, you will get this. So can I rewrite it as this? But can I say that this is nothing but when the function is applied only on U, plus this is nothing but when the function is applied only on V? Because when the function is only applied on U, you will get the first element as it is, second as it is, and instead of third, you will get 0. And when the function is applied on V, you will get first element as it is, second as it is, and third, you will get 0. So this is this. So I started with f of U plus V, and I proved that this is equal to f of U plus f of V. Now, this is my first part of the proof. I still have to prove the second thing. I still have to check for linear transformation, the scalar property. So let's do that. Second. To check this, I'm going to find f of Ku. So f of Ku is going to be f of K into U was what? A, B, C. Sorry. So this is going to be f of K into A, comma, K into B, comma, K into C. So this is going to be what happens when you apply a function on the vector. The first element comes as it is, second comes as it is, and third comes as 0. This is what it is doing. Whenever you apply a function on any vector, the property that is given to me is first element as it is, second as it is, and the third comes as 0. So this is what I am doing. So I just got this. Can I take K out common, and I can say that this is A, B, 0? But isn't this applying function only on U? So I have proved the scalar property also. So because this scalar property holds true, because this property holds true, therefore, I can say that f of x, y, z is equal to x, y, 0. This is a linear transformation or a linear mapping. Very easy. You just have to look for these two properties and check whether it is a linear transformation or not, whether it is a linear mapping or not. Now, take one more question and please try this. It's important from exam perspective. So you have a function, okay? This function is given from R2 to to R2. And what is the function that is given to you? The function given to you is x plus 1, comma, y plus 2. And you have to check whether it is a linear transformation. Please check this once. Just think about it. You're going from R2 to R2 and you have to check whether it is a linear transformation or not. Now, here is the thing. Let's try this out. You know, what it is saying is whenever you apply the function on any vector, xy, the result that you get is x plus 1, y plus 2. This is the result that you get. Suppose, to prove this, I can do the easiest thing. And the easiest thing is the following. I will go up and I'll do one more important property of linear transformation. What is an important property? One of the very, very important property of linear transformation or linear mapping is that it takes 0 vector into 0 vector. Which means whenever instead of the vector you put 0, 0, you should get 0, 0. That is an important property of linear transformation. Here also, if my vectors were 0, 0, 0, I would have got the function as also as 0, 0, 0. So, you know, an important property of linear transformation is that it takes the 0 vector into 0. Now, when I put my vector as 0, 0, I get 0 plus 1, 0 plus 2, which is 1, 2, which is not equal to 0, 0. So we can simply say, and this is one of the MCQs that can come, we can simply say that one of the property of linear transformation is that it maps 0 vector into 0. Because this is not satisfied here, it is not a linear map. Okay. Okay. Take another question. So now I am asking that I have a function and this function is defined from R2 to R3. And the function is in ST and this is given as 2s plus 3t minus s plus 5t 4s minus 3t. And the question is F a linear map? Please try this once. Now, so I'm doing all type of properties here, okay? I'm going to use the third property here. What is the third? What is one of the things that I showed you? That if I have to prove that something is a linear map, I just want to go ahead and write it in this form. Some scalar multiplied with the function plus some other scalar multiplied with the function. If I'm able to show this equal to this, then I automatically prove that it is a linear map. So I'm directly going to show it that. And that's the easiest thing to show here. So what I'm going to do is, this is my function that is given to me. Now let's go ahead and say that this can be rewritten as 2s minus s 4s plus 3t 5t minus 3t. Can I write it like this? I can, right? I've just split it. Now, even if you remember the addition of vectors, right? When you add two vectors, you add them component by component. So 2s gets added to 3t, you get the first element. Minus s gets added to 5t, you get the second element. 4s gets added to minus 3t and you get the third element. So this function can easily be broken down. So I had a function f of st and I've written it like this. I started with that. Now, can I also go ahead and write it like minus 2, 1, 4 into s plus 3, 5 minus 3 into t. So, I took this function and I showed it as a linear combination of s and t. Automatically, it is a linear transformation. Automatically, it is a linear mapping. So the answer is that yes, it is a linear mapping because it can easily be broken into the linear transformation of the two vectors s and t. Now, just one more thing that I want to kind of highlight here. I can also write this vector form into a matrix form. And how can I do that? I can write it as 2, 3, minus 1, 5, 4 minus 3, and multiply it by s and t. So please see here, this is of the order 2 cross 3. Sorry, 3 cross 2. And that's of the order 2 cross 1. So your answer would be of the order 3 cross 1. Exactly what I'm getting here. 3 rows and 1 column. So, you can also write this in this matrix format. And now I define very important property of matrices, that anything that can be represented in the form of a matrix definitely is a linear transformation. So please write down that matrices are linear mapping. Why? Because when you form these matrices in the background are just these linear composition or linear transformation of the vectors. So they are automatically linear mapping. Now, if we understand what is a linear mapping, then we should from here try and understand an important topic called kernel and image of linear mapping. Okay, now let's understand what is a kernel of linear mapping. So please write down. Let f be a function that goes from x to y, and this be a linear mapping. If it is a linear mapping, it satisfies those two properties that we just discussed. Now, in this case, the kernel of f is any x belonging to x such that f of x is 0. So for example, and we'll talk about it. So please write down first, kernel of x is any x that belongs to x such that once you have f of x, that gives you the answer as 0. And image of f is any y belonging to y such that there exists x belonging to x for which f of x is y. Ideally, this is the concept of very similar to range domain. So remember that, when I used to have two sets, then the image of a function is such that f of x is equal to y. Now, we are doing exactly same thing, but we are doing it in terms of vectors here. That's the only difference that I have. Now, let's take an example to make things clear. So, for example, I'm going to take my function f of x, y, z equal to x, y, 0. Why am I taking this function? Because I have already proved that this is a linear transformation. I already showed you that it satisfies the two properties. So, it is a linear mapping. This is proved. I've already proved you that. Now, if you ask me, first of all, let's talk about the image. And then we will talk about the kernel, or anyways, like. So, if you ask me what is the image of the function, then please see what is my function. My function is, you take a vector a, b, c, you put it in the function, and you get the response as a, b, and 0. You take any vector that has 3 dimensions, and you get a response which is 2-dimensional. The third dimension is 0. Right? Isn't it? So now it is saying that image of the function is any y such that f of x is equal to y. So what is this y? Such that you will get f of x equal to y. What is this? This is nothing but the image is your xy plane. Where is your image defined? Your image is defined in the xy plane. Just think about this. You took a vector. This vector was 3-dimensional. You put this vector inside the function, and the function transformed it to a 2-dimensional vector. It's still 3-dimensional, but the third dimension is always 0. If the third dimension is always 0, then it means that the z-axis is always 0. So you are always in the xy plane. So isn't the image just the xy plane? Isn't it defined like this? So the image of this linear mapping is simply the xy plane. It's an important question. Now, if I ask you what is the kernel of f? So the kernel of f is simply, what is it? What is the kernel saying? I want f of x equal to 0. I want f of x equal to 0. When will I get my vector as 0, 0, 0? Whenever you put any vector a, b, c inside the function, you get a, b, and 0 as the output. So the third part is already coming as 0, irrespective of whatever c you have. You have c negative or positive, c is always coming as 0 in the output. You just want to think about the first two also. You want to make these also as zeros for it to be the kernel, right? So that is possible only when you have a vector such that its first two values are 0, but its c can take any value. Because whatever c you put inside the function, the answer will always be 0. Students get confused here. A lot of the students in the MCQ, there would be a vector given 0, 0 as the kernel, and they will click on that. No, The answer is A and B should be 0. C can be anything, literally anything, because whatever C you put, the output will automatically be 0. So you don't want C to be 0 for the result to come as 0. For C, it is already transforming it into 0. So the kernel sorry, of the function is A, B, C such that A is 0 and B is 0 for any C. And the image of the function is A, B, C such that C is 0, which is nothing but the xy plane. This is how we go ahead and we define the image and kernel of the function. Very, very important. A sure short MCQ is going to come in exam from this part. So you should definitely practice this. It's important. Now, please write down few questions. Let's do few questions on this. Before we go to the questions, I just want to give you theorems. There are 2 theorems that we should know. Not necessary for exam point of view, but it may help you to solve the questions. So I'm just going to list them before we go to the questions. So theorem 1. Let the function go from x to y be a linear mapping. Then the kernel of function is a subspace of x and image of function is a subspace of a y. So we already know what is a subspace. A subspace satisfies the properties of the vector space, right? So I'm saying if I'm defining a function from x to y and let that function be a linear mapping, then we are saying that the kernel of the function, kernel means it's giving you 0, 0, 0 as the response. That is a subspace of x. And I'm saying that the image of the function, that is a subspace of y. Now please write down the second theorem. We don't have to use them. You should just know what is a subspace of what. Suppose x1, x2 and so on till xn, this span a vector space x. And suppose the function is defined from x to y is linear mapping. Let's define it from x till xm. Then f of x1, f of x2 till f of xm span image of the function. Let y belong to the image of the function, then there exists x belonging to x such that f of x is equal to y. Now this is very simple. You may think it is difficult. It is very, very simple. Please try and understand this thing. See, what am I saying? I am saying that, you know, I have x's that span vector space x. If they're spanning vector space x, which means that these x's together give you different linear combinations. So, which means that there will exist any x, which is nothing but a linear combination of these x's. So, ai, xi, I from 1 to n. Any new vector can be created from a linear combination of these x's. This is what it means, right? If it is spanning the vector space. So we understand this thing. Now, supposedly I am saying that this is given to me, that these x's span the vector space x. Now, I understand that y is defined such that y is a function of x. It's a linear mapping. This is how they have defined. Then I understand that because it's a linear mapping, I can say that y can be written as nothing but summation. It's a function of this new x, this. But this x is nothing but it's a linear combination of the existing vectors, existing x's. So you should be clear with the concept of spans. Okay. So this will be xi's, I from 1 to m. But if y is a linear combination of this and y defined the image, then clearly these vectors, functions are spanning the image because y is formulated by a linear combination of these. So I can simply go ahead and say this, that the vectors, again, these theorems too are not important, but I want you to kind of remember them. Span, image. Okay. Okay. Now let's go ahead and let me give you a few questions and I want you to try those. So write down. You're given a function which goes from R4 to R3. And the function is defined like this. F of x, y, z, t is x minus y plus z plus t. 2x minus 2y plus 3z plus 4t. 3x minus 3y plus 4z plus 5t. And you have to go ahead and find image of f, find kernel of f. Okay. Okay. Let's go ahead and do that. Now, how do you find the image of f or kernel of f? First of all, what I will do is I will write it in a better formation. So, let's just think of this as a transposed vector. So let's say supposedly that this is a transpose. And now what I'm going to go ahead and do is, just give me a second. Yeah. Now let's consider this to be a everything to be a transposed vector so that I can present it better. And I can write it like this: x minus y plus z plus t. 2x minus 2y plus 3z plus 4t. 3x minus 3y plus 4z plus 5t. Now you know what to do. So you will have x, 2x, 3x plus minus y minus 2y minus 3y plus z, 3z, 4z plus t, 4t, 5t. Okay. Now, this is going to be 1, 2, 3 of x plus minus 1, minus 2, minus 3 of y plus 1, 3, 4 z plus 1, 4, 5 t. Now, what is the question asking? Now, very simple. The question is asking about the image of the function. What is the image of the function? The image of the function is nothing but what you get out of the function. When you put some vectors inside it, what is the response that you're getting? Isn't it? So now if I go back and I go to this theorem becomes immediately useful right now. It simply says that the image of the function is spanned by individual vector functions. And what are my individual vectors? These are my individual vectors. So I started by this function and I showed that this function, and I showed that this function is a linear combination of these four vectors. So because this function is getting spanned by these four vectors, we can go ahead and say that these four vectors are nothing but this is f of the first vector, this is the second vector, this is the third vector, and this is the fourth vector. So I can clearly go ahead and say that these are the images of my vector. Simple, because they are going ahead and spanning my function. So I can simply say that the image of my function is nothing but these individual vectors which are spanning my function. So f of E1, f of E2, f of E3, and f of E4 span image of f and hence are part of image of f. Now the second question is, what is the kernel of f? So to find the kernel, I want everything to be equal to 0. So I want x minus y. You know, what is my function? My function is x minus y plus z plus t, 2x minus 2y plus 3z plus 4t, 3x minus 3y plus 4z plus 5t. I want each of them to be equal to 0. Isn't it? This is what I want. I want the image of my function to be equal to 0. All three parts to be equal to 0. But here's the thing. I have 4 vectors, right? I have 4 variables in a way. And, you know, if I have supposedly considered this, if I have to satisfy 3 equations in 4 variables, don't I know that one of them will be a free variable? So supposedly one of them will be a free variable. So let's consider this. What I will do is, from here I will bring it in the matrix form. 1, minus 1, 1, 1. To again refer to the previous lectures first. 2, minus 2, 3, 4. 3, minus 3, 4, 5. Just apply row echelon form to it. So, you know, if you apply the row reduced echelon form, you will get R2 goes to R2 plus 2R1 minus 2R1. So 2 minus 2 is 0, minus 2 minus minus 2 is 0, 3 minus 2 is 1, 4 minus 2 is 2, 1 minus 1, 1, 1, 3, 3, 4, 5. And now I can say R3 goes to R3 minus. Please do it only after you understand the previous lectures. 3 times R1. So 1 minus 1, 1, 1, 0, 0, 1, 2. And 3 minus 3 is 0, minus 3 minus minus 3 is 0, 4 minus 3 is 1, 5 minus 3 is 2. And now R2 goes to R3 goes to R3 minus R2. So I will get 1 minus 1, 1, 1, 0, 0, 1, 2, 0, 0, 0, 0. So which are the pivots that you get? you get only two pivots, this and this. So there are two free variables. Isn't it? Now if I put back x, y, z, t, so I am saying that z plus 2t and equate this to zeros. Z plus 2t is 0, then z is minus 2t. And if I say 1 minus y plus z plus t is 0, x, and I put z equal to minus 2t, so I get x minus y plus minus 2t plus t equal to 0. So I get x is equal to y plus t. So do you understand that x is defined in terms of y and t, and z is also defined in terms of t? So your kernel is not like the origin, like very simple one. Your kernel is x can take value y plus t, y can take any value, z can take value minus 2t, t can take any value. This is your kernel. You give any t value, accordingly this will be defined. You give any y value and t value, accordingly this will be defined. And once you get this vector, then whenever you will put this vector, the value will come out to be zeros for all three equations. So this is the kernel. So you can say that if you put t equal to 1, then accordingly your and y equal to 0, then your kernel will be 1, 0, minus 2, 1. If you have t0, y0, then 0, 0, 0, 0. This is also one of your part of the kernel, but this is also your kernel, and so on. So this is how your kernel will be defined in this. Okay, thank you.